Okay, so let's get going. Good evening, everyone. Welcome to today's asset colloquium. For those of you who are not from the DIFR family, asset stands for Advances in Science, Engineering and Technology. Essentially, we organize talks related to engineering and technology and other related fields on every Friday at 4 o'clock, just like what you're participating today. This, of course, is complements the other two colloquia that DIFR organizes, namely the natural sciences colloquium that happens on Wednesday, and also the mathematics colloquium that happens on Thursday. So today we have Professor Debdeep Mukhopadhyay from IIT Kharagpur going to speak on every contact leaves a trace, the side channel and microarchitecture attacks on modern crypto systems. Obviously, this is a very current and very important topic, especially in the world of all computer science, mathematics, and finance, and many other fields become so synonymous with each other in its applications. Just to say a word or two about Professor he's, in fact, I think all in all of IIT Kharagpur, he did BTech, MS, and PhD from IIT Kharagpur. Of course, he's a faculty in IIT Kharagpur right now. I contacted him last year at some time. Basically, he was recipient of the prestigious Science Award, which he won last year for science and technology. And also a fellow of the Indian National Academy of Sciences, INAE. Was awarded Kushla National Award from IIT Roorkee 2021, PhD Scholar in 2016, INSOI Scientist Award, and INAE Engineer Award, and also Associate for the Indian Academy of Sciences. As I mentioned, he is a professor in the Department of Computer Science. He actually initiated secured embedded architecture laboratory, which is focusing on hardware security. He had worked as a visiting scientist at NTU Singapore, visiting associate professor in Shanghai, assistant professor at Madras, and visiting researcher at the Tandon School of Engineering in the US. I mentioned, of course, his research interests are on the topic of cryptographic engineering, particularly in the hardware security systems, which we can talk about. He was actually recently interviewed by the Adversarial Attacks, as the title of today's talk says, on machine learning that infected competition. So, with a few words of introduction, we can very well look forward to very interesting and at the same time very informative talk from Professor. Over to you.
Thank you. Am I audible properly? Yeah.
Yes.
Thank you, Professor Satyanarayan, for this kind introduction and also for inviting me to this colloquium. It's my honor to give this talk. So without much ado, I would like to start with this topic, which essentially was already mentioned. Every contact leaves a trace, wherein I will try to talk about side channels and microarchitecture attacks on modern crypto systems. So to begin with, quickly speaking, the area that I work on is called as hardware security, which tries to bridge the gap between theory and practice. So we know that in the classical crypto world, we have got, say, Alice and Bob who are communicating with each other, and we have the like Eve or the Mallory who is essentially eavesdropping the communication. So, however, in real life, cryptographic theory has limitations, because of which there is an absence of, and because of this absence of theory for the reality, even like mathematically secure algorithms can leak in the real world. So often this leakage is in the form of what is called as side channel attacks, or side channels in the real world, through which a cryptographic module can leak to its environment in an unintentional fashion. So talking about designing secure crypto systems. Like if I make a statement, a theoretical statement, like let G be any like mathematical group where, say, a discrete log problem is hard, right? And this is a purely mathematical statement, and based on this, right, there are several crypto systems that have been developed. So in real world, if I talk about a practical instantiation of such a hard or notion of hardness, then based on that, right, we can develop several crypto systems. For example, like elliptic curve crypto systems is a very popular form of public key cryptography, which is based on ECDLP, or elliptic curve discrete log problem, which is believed to be hard. So this is a practical instantiation based on which mathematically strong cryptographic algorithms have been constructed. However, the point that I would like to highlight is that there are a plethora of attacks which tries to break real world ECC without even trying to solve this ECDLP problem. And that brings us to what are called as not only secure curves, but also safe curves as defined by Dan Bernstein and Tanya Lange. So that means, right, essentially in this process of translating from theory to practice, there can be several interesting, aspects which can crop up, and that essentially encompasses my journey from theory to practice. So in theory and practice are same, but in practice they are not. And this translation of theoretical constructs to practically secured instances is essentially what we try to deal with. In order to look into this, like make and break game and attacks and countermeasures, we set up this laboratory at IIT Kharagpur, which we called as Secured Embedded Architecture Lab around 2008. So before I go into my talk, I would also like to mention that this particular discourse of side channel attack is also an extremely practical field of study, and therefore our experiments needs to be ratified and ensured in the laboratory, and therefore we try to kind of develop a lab on side channels and the various other aspects of hardware security, and that pretty much brings our research into life. So with this quick background, I would like to start my talk, and today's talk I largely divide into three parts, essentially two major parts, where first I talk about or try to give an overview on side channel attacks. And in the second part, I will try to talk about microarchitectural attacks, some of the classical forms of microarchitectural attacks, and try to conclude with some of our recent findings. So to start with, when we talk about the present day world, we know that we are dealing with an interconnected system with billions of devices communicating with each other. But at the same time, while these ushering technologies like Internet of Things, cyber physical systems can really revolutionize the quality of life, but it also brings us, brings in us the aspect of security, without which it can have catastrophic consequences to mankind. In the Indian context, these kind of technologies also has got wide promise, but what we always need to keep in mind is that many of these solutions are often developed without security in their design process. So to hit the nail or to motivate this point, I would rather take your attention towards this paper, which was called as IoT Goes Nuclear, published in IEEE Symposium on Security and Privacy in 2017. So in this paper, the researchers, which are largely based in Israel, they tried to kind of look into, smart bulbs, which are called, which were commercialized by Philips at that time and were called as Philips Hue lights. So now, like among many other things in these smart bulbs, as they are called, I mean, they are essentially, like newer technologies of electric bulbs. The idea being that you can control and command those bulbs at your own, like based on your mood and temperament. But of course, right, you do not want your neighbors to start controlling and commanding these bulbs. However, researchers showed that there is a, there is a particular feature in these bulbs, which are called as over-the-air updates, through which, like the corresponding firmwares can get updated. And of course, right, anybody cannot or should not be able to do that. And in order to ensure security, there was a process of encrypting, signing, and uploading the corresponding firmwares, which was done based on an AES crypto system. More precisely, it was based on AES CCM mode, and it relied upon a 128-bit or 256-bit secured key. So if you talk about a classical, from the classical point of view, AES is a wonderfully designed algorithm. Okay, and till date, even probably after 20 years of research, there are no really glaring attacks on AES 128 mode precisely. So which can really, like conjure the key in practical amount of time. However, like if you, for example, what the researchers did is they took hold of physical possession of these bulb systems, and they tried to kind of analyze the corresponding, like electronics inside the device. And they found out that when the encryption, for example, takes place, if one observes the electromagnetic traces, then they can, like potentially do an attack, which is called as correlation power attacks or correlation electromagnetic based attacks, through which these keys can be divulged. And the moment the keys can be divulged, you can imagine that, you can, like virtually upload malicious firmwares, and you can completely create havoc in the lighting systems. So there is a very nice YouTube video for this work, where they show how they fly drones around the buildings of the premises where these bulbs are installed, and virtually at their will they can, like create an SOS signal in these lighting systems. And they also, like some more analysis to show that they can actually create a complete darkout for a city as big as Paris. So you can see that what basically this work shows is that there can be a potentially, like an attack surface, which essentially can completely create, like havoc in a system of connected devices. And that is why this paper is called as IoT Goes Nuclear and so on. So now in this talk, we will try to understand how these physical attacks work and what is the basis behind them. So therefore, right, this brings us to this topic of what are called as side channel attacks, which tries to, like exploit these kind of artifacts in the electronic systems, or in general, the computing systems on which your crypto is constantly running. So it could be your mobile devices, it could be your credit cards and so on, even your desktops. So how do we really address this problem? So if we think that this problem can be solved by cryptography, then we really do not understand what cryptography is meant for, and we also do not understand the problem. So this problem is not really with how the AES was designed or the crypto was designed, but rather how they're implemented on actual systems. So therefore, strong cryptographic algorithms are definitely important, but they are only the beginning of the story. So therefore, if you take, for example, a credit card and you are exchanging inputs and outputs, and your system is protected by an AES or an RSA kind of crypto system, then so far it is fine. But the moment there is a side channel information that is getting divulged, then they are not secure. Luckily, our credit cards that we are probably carrying with us nowadays have protections against such kind of attack vectors. So therefore, what are side channels? So side channels are covert channels which leak information which the designers of the crypto algorithms did not really consider. So it could be a benign looking if-else statement in your program, which can potentially leak information. So there are various kinds of side channel sources. So far, or classically, we have been handling crypto algorithms. There are the threat models and security goals, protocols, softwares, hardware, deployment and usage, and finally human users. So we all know that with humans, right, it is probably impossible to design a totally secure system with it, and we will not probably even try at this point. But what I would like to kind of emphasize is that traditionally we have been handling crypto algorithms, but side channel attackers try to deal with how the software is implemented and how the hardware is implemented and how the crypto runs on them, and what are the like impact of like when, for example, a software crypto engine is running on the timing behavior of your crypto engine. What is the behavior on power consumptions, EM radiations, how do you test your devices, the behavior under faults, all these kind of forms attack surfaces to a side channel adversary. So let us start with power-based side channels, which still even today remains one of the most, or I would say, major forms of side channel attack vectors. So in this particular slide, I try to show you, like the power consumption pattern when there is an AES kind of engine that is executed. So you can see very much that there are 10, like if you can count, like that out here, you will see that there are 10 jumps in this particular power trace, which is nothing but the power consumption pattern when the encryption engine is executing. So these 10 jumps actually correspond to the 10 rounds of the AES 128 algorithm. And you can very much, like read out that these 10 rounds are there inside the power trace or the electromagnetic traces. However, you can actually go down inside one of these rounds as shown over the right-hand illustration, and you can see that there are even more variations which are occurring inside the round. So now the question is, right, does this reveal information or does it reveal the secret key? So in order to understand, or the power attacks are in general divided into two wider classes of attacks. One which are called as simple power attacks, wherein the variations occur because of the operation dependence of power. For example, if I take the AES algorithm, we will find out that inside there are various operations. There are some linear transformations and some nonlinear transformations. The behavior or the variations on or the impact of these operations on power essentially varies, and that forms what are called as simple power attacks. So on the other hand, there is another, even I would say like more vital form of attack, which are called as differential power attacks, wherein they try to kind of exploit the data dependence of power. So this is what is called as DPA, and is even more potentially dangerous, because even if you have protections against simple power attacks, they can still be vulnerable against differential power attacks. So all these attacks were initially told or brought to public in this famous paper by Paul Kocher and their team in Crypto in '99. So how does a power attack work? So here is a very simple illustration of CPA. So this is the same attack that was used in the paper of IoT Goes Nuclear. So I will take some time to kind of explain how it works. So you can see here that for example, there is a say a plain text that is being encrypted. So note that these attacks can be observed both from the plain text as well as from the ciphertext. So imagine that I would try to explain this from the plain text side. So I take probably say 1,000 plain text patterns. So in this case, it is shown as D1, D2, and so on. And all of them are being encrypted by some unknown key. So the key is essentially unknown and not known to the adversary. So now what the adversary does is observes the first intermediate round of the crypto algorithm. So for the uninitiated, I would like to mention that in the context of AES, there is something which is called as an S box, which is essentially nothing but a nonlinear transformation. Okay, and this nonlinear transformation essentially forms a very important piece of the crypto engine. So, however, if you take the AES algorithm, you will see that the AES algorithm is kind of conceptualized as a 128-bit of data, and it is made out of 16 bytes. So now what makes these attacks very powerful is that they work on the principle of divide and conquer. That means they try to kind of recover each key byte one at a time, and therefore even if you scale the key, they still work efficiently. So in particular, let us concentrate on the first byte that you would like to recover. So this is, for example, the plain text byte shown over here, and there is a corresponding key that essentially is coming into play. So for example, if you observe that the key would be say also a 128-bit amount of information, but in particular, this particular plain text byte will interact with only, will only interact with one of these key bytes. For example, it will interact with this key byte. So therefore, right, this plain text byte will interact with this key byte and will essentially, lead to an internal data. For example, what will happen is that there is an S box that will operate on, say, this plain text byte. Let me call it as X, and will interact with this key byte, which is called as K. So now what will happen is that therefore, this S box will operate and will get XORed. So the X will get XORed with K, and what we will do basically is compute the corresponding S box. So now note that the output of this is a byte of information, and now depending upon the value of this output byte, the attacker will try to kind of apply a powered model. So this powered model are very prevalent forms of hypothesis in the VLSI community, which tries to kind of say that, okay, for example, for this value of the byte, what should be the amount of dynamic power that is consumed by the device? So if I take a very simplistic powered model to begin with, say what is called as a Hamming weight powered model, then that would imply that depending upon the Hamming, bits, that is the number of ones in the byte of the X XOR K, the corresponding dynamic power would be set. So this is what is called as a hypothetical power. So now the attacker will observe this hypothetical, or estimate this hypothetical power, and also keep in mind that since you are doing a side channel attack, when the actual encryption is taking place, you are also observing the real power traces. So the real power traces are also kind of observed. And what the attacker will now try to do is will try to correlate this hypothetical power with the power trace that has been observed. So note that the hypothetical power was estimated based upon the key that you guessed, because you made a hypothesis on the key. And depending upon the key hypothesis, you have got some amount of hypothetical power, and you try to do a correlation. So now you can repeat this key hypothesis because you are doing this attack in a divide and conquer fashion. You are trying to recover one key byte at a time. And we know that this key byte, for example, will take all, say 256 possible values. And you find out among the 256 possible values, which particular hypothesis or which particular guess of the key will give you the strongest correlation. So this way you try to kind of distinguish the correct key from the wrong key, and you try to kind of recover the key in a byte by byte fashion. So this is a very simplistic overview. Of course, there are more details, but I believe that this gives us an idea that this particular attack technique is a divide and conquer attack. And therefore, even if I scale up the key, these attacks will not really get thwarted. So here is an experimental evaluation on a simulated power traces. You can see that on the left-hand side, I show, how the correlation of the correct key stands out from the wrong key values. And that way you can distinguish and obtain the key values in a byte by byte fashion. On the right-hand side, it shows an attack where there is some amount of noise that has been embedded, but still, right, you are able to kind of filter out the noise and distinguish the correct key values from the wrong ones. So there are many works. So for example, you can also try to kind of observe this from the information theoretic point of view. And we make a study of how you can information theoretically explain this attack as well. So imagine that, as I said, the output of the S box or output of some kind of intermediate transformation of the crypto algorithm essentially is giving you a leakage. But when you are taking your probes and you are observing or monitoring the power consumption, there is also an amount of noise that gets in because of the measurement setup and so on. So you can kind of conceptualize this as if like there is a communication from the actual data to the output observable, and you can think of that to be happening in two layers or two channels. So now what the attacker can do, you can also try to model this in this fashion. So there is an observable distribution that you're observing, which is basically the power trace or the EM trace. And imagine that the output of the internal computation is essentially what I called as leakage. Now, as I mentioned in the previous explanation, the leakage depends upon the key byte that you are guessing. So you can imagine that all these leakage values are individual, like buckets or, like baskets, which has been shown in the illustration as L0, L1, and so on till Ln-1. So these are bins that we have kind of created. So these are leakage bins. And what you are now doing is you are taking an input X and you are distributing these leakage, these data or the, the corresponding data that you are accumulating into these leakage bins, depending upon the key that you are guessing. So now you also have an observable that you're observing, which is the power, which is the power trace in our case. And you can calculate the conditional probabilities like PO given Li and also PO. And from there, you would try to kind of infer the mutual information between the output observable and the leakage that you're observing at the output of the S box. So note that again, this leakage distribution depends upon the key. So the idea would be that that key, which will try to maximize this mutual information, is potentially the correct key. So you can also formulate this in a mutual information setting, and you can show that these attacks can be, like very nicely explained using this framework. So now I'll quickly talk about another form of sidechain attacks, which are called as fault-based cryptanalysis. So in this particular attack technique, you have got, imagine that there is a plain text and you are, like doing a normal crypto, and you get a fault-free cipher. And in another instance of the encryption, you induce a fault, and the fault can be induced by various mechanisms. For example, in our laboratory now, we try to do them by EM pulses, laser guns, and so on. But imagine at this point that there is a fault that has been induced and it leads to a faulty cipher. And so now the question is, right, when you get a faulty cipher, the common, like the intuitively what we may think, right, is that let us repeat the encryption again and go ahead. But what may happen is that a single fault instance can reveal the secret. So therefore, this essentially forms a very widely studied form of, like study, which are called as differential fault analysis, or what we call as DFA. And it tries to kind of analyze the nature of these faults and try to see that whether they really leak information. So again, talking about or taking the example of AES. So AES is a very widely formed study, like studied cipher. It's a very well-designed cipher, and therefore it forms, like a central piece of study for various kinds of attacks. So let us take the AES algorithm and in particular consider the last few rounds of AES. So imagine that when the 8th round of AES starts, there is an unknown fault that has been created inside the engine, and that fault essentially propagates down the cipher. So imagine initially, right, there is no knowledge about the fault because the fault is completely arbitrary. But then when, like the fault propagates, because of the internal transformation of the faults, you can observe that the faults essentially start to show some kind of interrelationships. For example, you can observe here that the fault here, as can be observed in this column, if you observe here, you will be able to see that, like although this is a 32-bit information, because each of the four, entries here correspond to a byte. So it is 32-bit of information. But the moment I fix the value of the fault here, the entire column can take only 2 to the power of 8 values. So that means that the entropy of this particular column reduces from 32 bits to only 8 bits of information. So therefore, if you go ahead, right, you will find that there will be more such kind of interesting interrelationships, as you can see here at the output of the 9th round mix column, which is an internal step of the AES algorithm. So what the attacker now does is it observes the output, or like output pattern, and then tries to guess the last few rounds, and from there work behind and try to exploit these interrelationships. Of course, there are some more challenges which comes in because of the key schedule and how how efficiently you can do this experiment. But our analysis shows that a single fault can reduce the AES key size to only 256 values with a time complexity which is proportional to only 2 to the power of 30, AES operations. So this shows that a single fault may, end up in revealing the key, and therefore, right, a double fault will probably even not be required. So interestingly, very recently, this attack was shown very powerful against, and a version of Intel processors were called as Intel SGX, and this attack was called as Plunderbolt. So in this particular attack, the adversaries created this single byte fault by manipulating the voltage frequency scaling which is present in our modern day computing systems, because of various reasons like low power and other energy efficiencies, and showed a little bit of undervolting can really create a lot of trouble. So in this particular example, or in this particular attack, they retrieved the AES key using the single fault attack that we just described. And interestingly, right, Intel has right now, deprecated this version of their processing systems. So this brings us to how do you really counter against such kind of adversaries. So there are again, a large amount of fault tolerant architectures which has been developed. Some of them are based on what are called as detection-based countermeasures. So these are more of classical fault tolerant techniques. There are some more dedicated techniques which are called as infective countermeasures, which tries to kind of diffuse the faulty patterns and make them unusable. But one of the questions, right, that probably industry faces is how do you really test your countermeasures? How do you really know that they are indeed secure? So in one of our works, we try to develop a black box test methodology for fault tolerant architectures. So in this particular, effort, we basically take a protected cipher and we try to kind of develop a simulation-based framework through which you can understand that whether there is a potential leakage with respect to fault attacks. So I will try to give a very high level, idea behind this method. So in particular, what we try to do is we try to, model the mutual information between the output differential. So note that here the output differential means that it's basically the difference between the correct output that you will probably get in a fault-free execution and the faulty output. So now what you want is that the mutual information between this pattern and the secret key, okay, should be essentially 0. So equivalently, one may also kind of, show that it also is equivalent to show that the mutual information between the output differential and the faulty pattern is 0. So therefore, the differential should actually reveal no information of the key and equivalently about the fault, because even if the fault is leaked, one can reduce the key space and obtain the secret key. So now how do you really measure this kind of mutual information in a very simple manner? So what we try to do is we try to kind of develop a framework using, so we call it as a deep learning based leakage assessment technique. So what we do here is as follows. We take the encryption system and we try to do simulations, and the simulations are done with pairwise fault patterns, and we obtain faulty ciphertext, and then this output data that we accumulate, you try to develop, give binary labels depending upon whether it falls into the fault class F0 or whether it falls into the fault class F1. So now what you want is you want to kind of, train a corresponding machine learning model, and then, evaluate that whether the machine is able to distinguish between these output distribution. That means whether the machine is able to kind of say that whether by seeing the, output data, it is able to kind of understand the correct label, whether it comes from the world of fault 0 or whether it comes from the world of fault 1. The idea being is that if the machine is able to kind of do this with a probability which is significantly deviant from 0.5, which is in the random case, then there is a potential leakage of the fault value and equivalently of the key. So we try to develop an automatic framework and through which, analyze various such kind of crypto protections and try to see that whether they indeed leak in the real world. So therefore, right, I mean, this is a constant game of, trying to develop new crypto systems which are secured against side channel attacks, and also try to see that whether they are really secure. So we also try to kind of, develop a tool which, where we bring all these things together and develop a tool which we call as ESP Anveshak, which is a side channel evaluator and analyzer. So I think I would try to give a, an overview of our laboratory setup. I hope that the audio is
Debdeep, did you mean to share a video?
Yeah, so is the video playing?
We can only hear the audio.
Okay.
Yeah, it's we are able to hear the audio, but maybe the thing was not yet started or something.
So can you see? Can you see the line overview written over in the slide?
Yes.
Overview.
Yes.
So it will play actually. Yeah, I think.
Yeah. Audio is good.
Yeah. worked? I mean,
Yeah, it was quite clear. Yeah, both ideas.
okay. So this brings me to the, like the second part of my talk, which is on microarchitecture attacks. And so in this, so far I was talking about sidechain attacks on embedded systems, but what really happens on, like your computing systems, like maybe desktops or your laptops. So indeed, right, I mean, there is also a gap between the hardware and software, and particularly like this event of what attacks which are called as Spectre and Meltdown has showed that indeed these microarchitectural attacks, right, can really be quite catastrophic. So in order to quote like the Bruce Nair, who is a famous crypto reporter, says that fixing them requires either, like a patch that can result in a major performance hit, or it is probably impossible and requires a re-architecture of various kinds of internal systems, which can, like take us back probably 20 years. So I'll try to kind of talk about this and, like try to kind of highlight the importance of a holistic approach which is needed for building secure systems on architecture-aware models of leakage by taking this example of our old work that we published in InnoCrypt 2009 with a group of Japanese collaborators. So in this particular work, we try to take it what is called as timing attacks on block ciphers. So pretty much the ciphers like AES kind of systems, and try to see what microarchitectures have to do with them. So when we talk about microarchitectural based attacks, here we are dealing with, like the various architectural artifacts like cache memories, branch predictors, like your speculative executions, your memory architectures, and so on. So there are so many things that can, like gradually come up, because predominantly these artifacts were developed from the point of performance, and we often see that they conflict with security. So in particular, I will try to take a focus on cache attacks and try to develop, show how microarchitectures can be quite serious. So let us consider that there is a, like a processor on which there is an crypto is executing, and imagine that there is a secret key. And as we know that in most of our systems, we have got the cache memory, which is a fast form of memory, which tries to bridge the memory wall between the slower main memory and the, like the faster, like registers and your CPU cycles. So we know that when there is a cache hit, the access time is less, there is less amount of power consumption and so on. Whereas if there is a cache miss, the access time is high and there are more manipulations that takes place. So what if, right, like an attacker is able to kind of observe and distinguish between these cache hits and cache misses? What has that got really to do with security? So let us take an example again of the AES kind of cipher. And often, right, for software designs or software implementations, they are implemented in order to make them fast, they are implemented using table lookups. So if you see, for example, the OpenASL distribution of AES, I mean, classically, they were implemented using tables. And the moment, right, you implement them in tables, there are a lot of memory lookups that takes place. And therefore, right, corresponding the memory and the memory footprint and the cache footprint comes into play. So in particular, if you take the AES or think about, like a part of the cipher. So in this case, I, like show that this is the one part where there is a key, say K0, and in another case, there is a K4, which is another part of the key. You can imagine that there are two different bytes of the key. So classically, they are independent. That means, if you think of the AES, right, there are 16 bytes of the key. All the 16 bytes are kind of independent. That means if I tell you information about one of the bytes, ideally, right, there should not be any information about the other byte. And that's why, right, you get the entire 120-bit amount of entropy. However, imagine that there is an encryption that is taking place, and because of the table lookup, in this case, you are doing an XOR, which is the key mixing part, where you XOR the P0 part with the K0, and you make a table lookup. That means you kind of look at a memory location, which is corresponding to, say, the XOR of P0 and K0. Now, in the next part of the cipher, when you are processing P4 and K4, you are also making a table lookup at a location, say, which is an XOR of P4 and K4. Now imagine that there is a cache hit, and because of the cache hit, like the time is less, and there is an astute adversary who is able to observe this timing and distinguish that whether there is a cache hit or there is a cache miss. So what does the phenomena of cache hit tells us? It tells us that the address, or maybe, like you are trying to kind of look into the same cache line when you are XORing P0 and K0 and P4 and K4. And that immediately means that that K0 and K4 are not independent, and there can be relationship between them. Note that for most of these attacks, we assume that the adversary knows the plain text, and therefore, knowing partial information about K0 reveals some amount of information about K4. And likewise, you can form some kind of, even some kind of exclusive equations, or you can exclude some possibilities in the case when there is a cache miss. And that means that, the overall entropy of your key system reduces because of the ability of the attacker to distinguish between a cache hit and a cache miss. So this is the broad idea behind what are called as cache attacks. And one of the classic forms of attacks were shown by Oswick and their colleagues, where imagine that there is this is an AES, imagine that there is a spy which comes in and, accesses the microprocessor, and it fills the cache with some kind of random data. And in the same kind of system, the AES also runs, and that's a victim that you are targeting, and that also kind of makes an access to the various lookups and evicts some amount of data from the cache. Next time when the spy comes in, right, and if you're able to kind of distinguish between the cache hits and the cache misses, the spy is virtually able to know the footprint of the AES engine. And that means that it can try to launch various kinds of attacks as we just now described. So there was a very interesting paper by Dan Bernstein in 2005, which was called as cache timing attacks, which tries to show that even such kind of attacks can be mounted in a remote manner. So for example, imagine that there is a server which is running an encryption software, and there is an attacker who is probably setting up a TCP kind of network, sending data and observing the corresponding encrypted packet, but also observing the time. And using these statistics, it tries to do an attack on the remote server. So in this particular experiment, imagine that again AES is your target, and there are 16 bytes of the input of the AES engine, and you are kind of giving choosing some value of one of the bytes, and for the other bytes you are giving some random inputs. So now what you can do is you can observe a timing characteristic by taking different values of this P0 value, and now depending upon the value of this P0, you can observe the timing that is required for the encryption, and you can get this what we call as a timing characteristic. Interestingly, what Bernstein shows is that if you set an all zero key, and if there is an unknown key, you will find out that the timing characteristics pretty much look the same, except that there is a small amount of shift, and therefore if you correlate, then you will be able to observe the secret key. So this attack was shown on AES, and you can actually mount it on OpenASL implementations, and in particular, right, that opens up various kinds of timing attacks that were possible on the original AES distribution. And luckily nowadays, in most of the Intel machines, we have got what are called as AES NI, and therefore because of the hardware support, these kind of attacks should not be possible, at least when you are running AES crypto and not some other ciphering algorithm. So in particular, these OpenASL distributions had a 4 kilobyte table, and we tried to kind of investigate why this attack worked. And you will be able to see that there is a very nice distribution of the number of misses, and we believe that the cache attacks work because of this varying execution time. Now, what happens when you implement AES with a smaller table? Say you can also implement AES with only the S box being supported in the tables, where the other operations are done using instructions. The moment you do that, then that means you can imagine that since it's a smaller table, in very few amount of operations, the entire table gets loaded, and therefore after that you get all a cache hit. So you'd expect that your encryption time is a constant, and in particular in this graph you can show that the expected number of cache misses is always 4, and therefore it was widely believed that such kind of small table based ciphered implementations are secured against cache timing attacks. So, and in fact, right, if you do run the Bernstein's attack on small table implementations, then you get variations which are very small, and therefore it was believed that these attacks are are difficult. So in one of our works, we try to kind of look into this and try to see that whether they are indeed secured. And in this process, we came out, we observed that in fact, modern day microprocessors are always, I would say armored with several kind of artifacts. Many of them are for improving performance. And it turned out to be one of our first, lessons to see that many of these modern artifacts can actually conflict with security. So in particular, we try to look at one of the features in modern day processors, which are called as out of order loading of a cipher. So imagine that, and I will try to kind of highlight quickly that why it is relevant for a cipher operation. So imagine that there is an AES kind of crypto running, and there are several S boxes, as I mentioned. In particular, for AES 128, there are 16 S boxes in the first round. All of them are independent. Now, in modern day microprocessors, we have this feature that if, for example, when you are doing these S box lookups, and if they result in cache misses, then you can service them in parallel. But if there is a dependence, like for example, if you consider round 2 and you consider the dependence between round 1 and round 2, then you cannot parallelize them. So what has that got to do with the timing of your ciphering operations? So imagine that, think about this, your cipher that I was just mentioning about, where the cipher is implemented with small tables, where it looks like as if the number of cache misses are always a constant. So consider a 5-round block cipher. In both cases, there are 4 cache misses. So this is exactly the scenario that you will probably see when you have a small table-based cipher implementations. However, what varies right across, say, the encryption run E1 to encryption run T2 is the distribution of these cache misses. Now, does this really, so in a classical sense, where there are where such kind of overlapping and out of order executions are not supported, both these two executions will probably give you similar amount of time. But the moment you have this artifact, you can imagine that the timing for E1 will be lesser than the timing for E2, because the first round, which has got 2 cache misses in the first execution, can be handled in parallel, which cannot be done in the E2 or the second execution. And that means that you are still getting some amount of, from the timing information, you are getting some amount of information about the footprint of your execution or AES execution or encryption execution, which you can try to exploit in your attacks. So in particular, we also try to look at some other artifacts like the hardware prefetchers, which tries to kind of make your or rather bring data ahead into the cache memory, and therefore reduce the number of cache misses. And we showed that we in particular studied some classical prefetching techniques like sequential prefetchers and arbitrary type prefetchers, and show that they are also responsible for this timing characteristic, which you can use or exploit to perform timing analysis. So therefore, the summary is that for modern day cache misses, the execution time not only depends upon the number of misses, but it also depends upon the distribution of misses. Interestingly, hardware prefetchers also can cause variations in the timing profiles, which can be exploited. And the distribution of misses often depend upon the key, so the execution time also depends upon the key. So as a demonstration of this, we showed that Clefia, which was a cipher which was designed by Sony, right? And we showed that you can, although they were implemented with small S boxes, in particular, they were implemented with 256 byte tables. One can still launch an attack where the initial learning phase takes around 1,000 seconds, but in the second phase, you can do this attack and still recover the entire key. In particular, we showed at that time that this attack worked on Pentium 4, Intel Atom Xeon Core 2 servers. At that time, those were the most prevalent computing systems, but the attacks failed on Pentium 3 because we believe that the artifacts like out of order execution and handling the cache misses in parallel were potentially not supported in the older generation microprocessors. So quickly, I will round off my talk with some very recent attack that we were working on. So this particular attack we called as RASL, or return address stack based sidechain attacks. And in this particular attack, we try to kind of exploit a feature of an operating system and show how their interrelationship with an artifact in the processor can lead to information leakage. So this attack we called as RASL, and we show how an entire digital signature key can be stolen using this attack technique. So some quick words about the deadline scheduler that we target. So deadline schedulers are some schedulers which automatically preempts a process from the CPU after its request expiration time, and they are often applicable for real-time operating systems and embedded systems and so on. The interesting part is that you can actually set the parameters of the deadline schedulers using capsys, which is not necessarily a root privilege, and you can actually kind of create a synchronization with a spy processes so that your victim or the ciphering algorithm that you are targeting can preempt after a certain amount of operations, so that the spy can very granularly look at the timing pattern of your victim encryption unit or encryption system. And this has not really been studied much before. And the other artifact that we try to look at is what I called as the return address stack. So the return address stack is a special purpose stack that is present in our modern day computing systems. the objective is to reduce the number of misses or branch misses that you will get if they are not handled in a separate manner. So in particular, you can imagine that there are several function calls that probably will be there in your normal programs, and if you are using the standard techniques of branch predictions, then they will often encounter several branch misses. The reason being is that the return address that you see for which are corresponding to these function calls are called from different locations in your program, and therefore the history of your older for say a previous return will not work in predicting the branch target for a following return instruction. And therefore, in order to reduce the number of branch misses, the processors nowadays have a special hardware stack, which is called as the RAS, or the return address stack. So now we observed a very interesting phenomenon in the return address stack, that is that the return address stack has a small hardware footprint. So for example, like in this case, it has got the size of the return address stack is only 16, and one can create a situation where the entire RAS is filled up, and therefore the moment there is your victim process essentially does a function call, then the corresponding data in the return address stack gets removed, and therefore one can observe that by observing a timing, you can kind of understand that whether the victim is executing a function or is it not executing a function. So what I mean is that if you, for example, set or create a program where there are, say, nesting of function calls, then the moment you have, say, imagine that the return address stack has got a size of 16, and you do 16 nestings of the function. So that would mean that the entire RAS gets filled up. And if you are making a 17th function call, then the oldest function, the return address, is removed from the stack, and therefore there is an increase of timing because of the ensuing delay that will come in terms of predicting the return address and so on. So now we try to use this timing difference in conjunction with the deadline scheduler and try to show first a covert channel. Now this is another thing that is very important in developing secured systems, where you need an isolation between the various kinds of endpoints. On the other hand, the attacker always tries to create a covert channel. So in particular, in this case, we show that we can create a covert channel quite easily. So imagine that there is a program or a function which is essentially serving as a transmitted program. So there is a secret data that you want to kind of transmit depending upon a function call. So that means if that bit that you want to transmit is 1, you make a function call, else you don't make a function call. Now, there is another process which is probably in an isolated location, but since it can observe the timing, and from the timing, it can understand, as I mentioned, that it has, imagine that the receiver program has filled up the entire return address stack, and is again observing the timing to understand whether the transmitter program essentially is calling this function, and that means that it is wanting to transmit a bit of 1. So therefore, we can show here that we can get a very accurate covert channel in this manner. And the next thing that we try to do is to see that whether you can really make an attack work and observe the signing key. And I'll not really go into in depth behind this technique, but on a very quick description. I mean, we try to target an OpenSSL ECDSA, which works on a very standard P256 curve, and show how can one perform a Russell-based attack to obtain the entire signature key. So one thing that I would like to kind of quickly mention is that when you are doing a signature, every time there is a nonce that is getting generated, and the nonce kind of is an ephemeral amount of entity. So now we need to kind of do this attack and recover, the nonce. But note that the nonce, since it is changing, it is very difficult to observe the nonce exactly in its entirety. So what we do is we employ Russell, and we recover, we do it what is called as a template matching phase to recover partial amount of information about the nonce. In particular, we recover the 6 MSB bits of the nonce, and then we follow it up with a lattice-based attack, which is quite well known in the literature of such kind of systems, where we show that through which you can show that in an offline phase, which is probably which requires less than 1 hour, you can recover the entire signature key. So this attack shows, how a combination of an attack vulnerability in your operating system and like in the architecture, which is in this case the return address stack, one can observe or obtain the entire signature key. So with this, I think I'm running out of time. So I would conclude, like by saying that sidechain attacks expose a gap between theory and practice of crypto. We try to kind of extend sidechain attacks not only for embedded systems but also for like our computing systems in the form of what are called as microarchitectural attacks, which tries to encompass the intersection of architecture and computer security. So architectures have been developed predominantly with performance in mind. We have got cache memories, prefetches, out-of-order executions. Nowadays, speculative executions have also been shown to be responsible to what are called as spectre and meltdown. Interestingly, Intel's stock fell by around 3% because of the, when the news of spectre and meltdown was informed. And therefore, design for security along with other objectives is getting more and more important. So it's a good time to think about a clean paper design, particularly with RISC-V around us. And I would like to kind of conclude with this viewpoint from John Hennessy and David Patterson to show that we have looked into several aspects, but probably it's a good time to look about microarchitecture security. So before I conclude, I would like to talk about this conference that we do every year in India. So if you are interested, please participate. And I would also like to mention quickly that every contact leaves a trace is what I started to say, but I hope that I have been able to motivate that every computation leaves a trace which the attacker tries to observe. So with this, I would like to say thank you. And if there are any questions, I would be happy to address.
Thank you, Professor Debdeep, for a very, very interesting, very illuminating, at the same time taking across. This is a kind of field we were not, I must say, exposed to. I mean, we keep hearing about cyber attacks in general and the computation, communication, etc. But these aspects that you and your group have studied, I think has really opened up a lot of new insights into what's really is at the cutting edge of this particular field. Are there any questions to the speaker? That maybe this is something which was not discussed today extensively, but you did mention in the passing quite a few times about the connected devices, the IoT devices, and especially the self-organized networks where the devices, the power is at a premium. So many of them are actually systems which work on, let us say, solar power and so on. So building a full-fledged security, onboard security systems becomes quite out of the reach for such devices. And so there is this concern about the network security of these systems. Can you say a few words about what are the advances field in which it is heading to as far as this is concerned?
Right. So yeah, you mentioned a very important point. I mean, one of the reasons why many of these IoT subsystems have insecure, techniques is not that we really do not know how to make crypto, but simply is because crypto often can become quite costly. So I think that there are two directions of in which people have tried to kind of address this. One is, of course, like trying to make crypto as less expensive as possible. So that means that you typically try to make them light, as light as possible. So therefore, there is this entire field of what is called as lightweight crypto, where you try to make the crypto consume less amount of energy, power, and take less resource. On the other hand, there also has been work on what are called as unconventional crypto. So in particular, we try in our group to work on constructs which are called as physically unclonable functions or PUFs. So many often, they have the promise of what are called as keyless crypto, where there is not really a full-fledged crypto which is executing, or maybe even if they are executing, they are taking, like less amount of resources. So probably if your hash function, and you have got, say, a physically unclonable function based root of trust, you can, like have a reasonable amount of, say, like authentication or the key agreement that can, like suffice in many real world applications. So I would say that there are usually, right, at least what the crypto part is concerned, right, you typically try to, like work by, like having a small hardware root of trust, and therefore, and on top of that, try to develop a minimalistic amount of crypto.
Yeah, thank you for throwing light on. I mean, one doesn't often hear these aspects, what you mentioned, particularly the low weight crypto systems, which now I think are getting into the main IoT systems, especially which are, a little bit strategic, or you can say, I mean, the systems which are generally amenable for attacks and so on. So, are these now, these systems are something still a research topic, or is there something which is already commercially available for the IoT systems?
I would say like lightweight crypto is an ongoing, like, of course it is in the research, but like there are many techniques which are pretty standardized nowadays. So for example, like we talk about AES, there are, like bunch of lightweight crypto algorithms which are quite well studied, like present, and they're following generation ciphers. And nowadays, there is also from NIST, there's an effort of standardizing what are called as authenticated encryptions, which are also, like developed with lightweight perspective in mind. And on the other hand, right, of course, I would like to say, when you talk about puffs, like physically unclonable functions, there are different categories of puffs. For example, there are some puffs which are used as key generators, and they are often based on what are called as SRAM puffs. So those puffs are commercialized. So there are companies which actually, like sell puffs, and therefore they are pretty, I would say, like ready in terms of market. But at the same time, there are also other classes of puffs, like which are called as what we call as strong puffs. They are developed for, so that the primitive itself can, like help you in terms of authentication and so on. But I would say, like those puffs, they are also challenged by like things like machine learning attacks, and also their corresponding reliability. So I would say, like the authentication based puffs are something that are very promising, but at the same time are being widely researched as of now.
Okay, thank you very much. Are there any more questions from Zoom or YouTube audience? Okay, I don't see any more questions. So once again, on behalf of all of us at TFR, and also the participants of this colloquium, I'd like to thank Professor Debdeep for his very, very interesting, and I think the colloquium, which will also kind of open up quite a few interesting problems for graduate and other master students. Thank you very much for the very insightful.
Thank you.
colloquium.
Thank you also. Thank you all, everyone, for this invitation. Thank you.
Thank you. Thank you.